Hello, my name is Rodrigo Cofré. Thank you very much to the organizers of Toponets 2020. I'm going to present a joint work that we titled Dimensionality Reduction of High-Order Signals via Hyperharmonic Modes. So this is a joint work with Aníbal Medina, Fernando Rosas, myself, Sebastián Rodríguez, and Pedro Mediano. The usual way in which multivariate time series are studied is just considering pairwise correlations. So the structure that used is the graphs. And the idea here is to go beyond pairwise interactions and consider higher order interactions. So when more than 3 random variables are interacting, more complex phenomena can be captured. For instance, the synergistic high order relationships that take part in the whole but not in the parts. To quantify these high order statistics, a usual way is to consider the extension of the mutual information. This is a work done by Fernando Rosas, Pedro Mediano, and collaborator in 2019 in the cited paper. So there are at least 3 ways to extend this notion of mutual information. One is called the interaction information, the total correlation, and the dual total correlation. And there you have the formulas. So something interesting happened if you consider the difference between the total correlation and the dual total correlation in system of n random variables. And is that you can say if the system is dominated by the redundancy, just looking at the O information. If they are positive, you say that the system is dominated by the redundancy. And if it's negative, you can say that the system is dominated by the synergy. This measure is similar to what James and collaborators call local exogenous information or barimutual information. And the sum of the total correlation and dual total correlation is similar to the Tononis-Borns-Edelman index. The problem when you consider several random variables interacting is that the structure of the hypergraphs are too large. So we need efficient way to represent signals on hypergraphs. The question is, can we do dimensionality reduction without losing a global structure? And can we transform our canonical base without sacrificing the global structure? So the way in which we do that is considering a geometric simplex using just low order information. We associate to each node a random variable. The weight of the edges are the mutual information, and the hyperedge weights are the average of this mutual information. So for instance, the weights to the triangle is the average weight of the mutual informations, which are the faces. And then you can consider a tetrahedron, and the faces of the tetrahedron are these triangles, and you take the averages of the mutual information, and this is the weight of the tetrahedron. And in this way you can build the whole geometric simplex. On the other hand, we have the higher order signals. You consider all the subsets of size 3 and compute all the omega informations, and you can do the same for all the subsets of size 4 and so on and so forth. And these quantities can be arranged in vectors in the canonical basis that we call omega and S for the S information. So the workflow is the following. We consider the multivariate time series. On one hand, we compute the geometric simple just using low order information. And on the other hand, we compute the signals that are these vectors with all the O informations of the triplets and fourplets, so on and so forth. So with the geometric simplex, we can compute the Laplace operator in the usual way, considering the boundary operator and the weights of the hyperedges. This Laplace operator or Laplace matrix for each dimension can be diagonalized, and then we consider the basis of the eigenvectors are the Fourier basis, and we can project our signals, which are these vectors, in this new basis. As a cases of study, we use 6 symphonies of the latest symphonies of Joseph Haydn. Each is composed by 4 movements. These are signals composed by 13 values. So the alphabets take 13 symbols, so 12 tones plus silence. To assess the compressibility properties of the transform signals, we consider the coefficients in the canonical basis of our signal, and we call them alpha E, and the coefficient in the Fourier basis called beta E. We consider the explained variance of eta, eta being either alpha or beta, as the square of the coefficients divided by the sum of the square of the coefficients. We consider the compressibility ratio as the log of the quotient of the explained variance of in the Fourier basis divided by the explained variance in the canonical basis, and then the cumulative explained variance as the sum of the explained variances. So when we consider the compressibility ratio of the first coefficient, averaged in all movements and symphonies, we see that the S information compress better than the O information, which is expected as the synergy, it's harder to compress, which is the negative part of the O information. And in the plot in the right, we see that the cumulative explained variance averaging all movements and symphonies and dimensions, we see that the compressibility of the Fourier basis is much better, in the sense that less information is lost when projecting in few components. So we provide a new framework to quantify high-order interdependencies as high-dimensional signals, and we provide a low-dimensional representation using tools of hyperharmonic analysis. So thank you very much.